We work for Antithesis, which is a company that has built an autonomous testing platform and to help make software testing better. And if you don't know what autonomous testing is now, well, hopefully you will by the end of the talk. So we titled this talk, Are Your Kafka Guarantees Guaranteed? But really, it's not just Kafka, right? We're talking about all software. And whatever software you build, when you build it on top of a streaming platform like Kafka or Pulsar, it's important to know what the guarantees of those platforms are because they inform the guarantees of your software. So let's think about, as we think about how we're going to test whether our guarantees are actually guaranteed, we're going to use two things to think about this. The first is property-based testing, which some of you may have heard of before, but it's usually more of in an academic setting, and we're going to hopefully make it a little bit more approachable and presentable. And the second thing is autonomous testing. So when we think about guarantees, it's important to know what we're actually guaranteeing in our software. So if you think about some of Kafka's guarantees, one of them is that message offsets always increase. So if you have a topic with partitions, as you send messages to the topic, the offsets will always increase. Some of Kafka's other guarantees depend on how you configure it. So for example, you might have an emphasis on availability. So one of your guarantees might be the cluster is available as long as most of your nodes are up. You can always, produce or consume messages from the cluster. Or if you're focusing more on consistency, you might want consistency guarantees that Kafka provides. So one of those would be no written messages are lost. So any message that makes it to the cluster won't get lost. It will be able to be consumed by the consumers. So then when we think about building applications on top of Kafka, we can take those guarantees and sort of internalize them for our own needs. So for example, if you're building a financial services platform on top of Kafka, you really care about the consistency and configuring Kafka to be consistent because you always want the transactions that happen in your system to be consistent. You want your bank account to say the same number on your phone as it does on the bank's servers, right? But if you're doing something like logging or metrics, you care more about availability. You don't necessarily need the most up-to-date information, but you always need to be able to access it. So again, the guarantees of your software depend on how you've configured your streaming platform and what those guarantees are. And that's great. We can say all of these things that we want to be true about our systems, but how do we prove that our guarantees are maintained? That's where actually the rubber meets the road, right? I mean, you can just throw your system into production, but then your customers are the ones telling you that your guarantees aren't maintained, and that gets really expensive really quickly. So we want to test, right? It's all about testing. It's everyone's favorite topic, software testing. But Kafka is a distributed system. Testing distributed systems is complex. So we're going to talk about a simpler example to try and motivate some of our thinking here. So we're going to talk about Super Mario Brothers. It's a great old classic game, one of the first Nintendo games. It's a platformer. If you have ever played it, this is what the first level looks like. So you start here, and you kind of go through the level, and your goal is to get to the flag. And eventually, over time, your goal is to get to the final world, the final flag. So as we think about what could Super Mario Brothers have to do with Kafka testing? Well, first, let's think about what are the guarantees that Super Mario would like to be true for their game. The first thing is that as you progress through the level, you only go to the right. You can't go backwards. You only go to the right. The second is that Mario can't go through obstacles. So like these pipes, Mario will have to jump over those pipes. He can't go through them. Same with walls, same with other things. And the third thing is that you should always be able to beat the game if you're good enough. Like you'll never get into a state where you're trapped, you have to reset the game. Wherever you are in the level, there's always a way to get to the end of the level. Okay, so that's great. These are the guarantees of Mario. What does it have to do with testing? Well, let's think about example-based testing, which is the software testing that most of us sort of learn in school or when we're first on the job. Think of this as like unit testing or integration testing. So example-based testing means you're given an example and you test whether that passes or fails. So that means we get a specific input under specific conditions, and then we see a specific response from our system. And then that response tells us if our test passes or fails. So for Mario, an example-based test might look like this. This is a series of inputs, jumps, moves to the right. He successfully gets to the end. All right, so if we think about our guarantees, well, the level always progresses to the right. Okay, that guarantee is upheld. Mario can't go through any of these obstacles, so that guarantee is upheld. He has to jump over them. And third, he makes it to the end of the level, that guarantee is upheld. Great. But of course, we are talking about Kafka, so we're going to look at an example-based test for Kafka as well. This might be an example of a unit test you might write in very bad pseudocode. So we have a producer, we have a message, we have a topic, we try producing the message to the topic, and then we do some sort of validation to confirm that that was successfully happened. Or if you're using an LLM, this might be what your test returns. Always returns true, right? That's great. Just kidding, don't write unit tests with LLMs. But what happens when your system changes? So we saw with Mario that this is one path, but there are many paths he could take, right? That would get him to the end. You could, instead of doing a bunch of jumps right here, he could just run. In order to test all of the different paths, that would take a huge amount of time because every step along the way, he can choose. Does he run? Does he jump? Does he move backwards? And then if the level changes, your test suddenly fails because where he was jumping before in the pre-planned sequence, now there's a wall in the way and he will be stuck forever. Similarly, in a distributed system like Kafka, if something changes underneath in your system, you decide to re-implement something or redo your database schema, that means you have to regenerate all of your tests, or else you just start ignoring your tests because you say, oh, it's a false positive. But then what happens is you either spend a lot of time rewriting your tests when your system changes, or you just ignore the results of your tests, in which case you actually could have really big bugs that are hiding from you. So instead of example-based testing, if we look at something like property-based testing, this kind of helps us get out of that tight coupling between what our tests say and what our system says. So instead of an example where you look at a specific input, a specific condition, and a specific response, property-based testing lets you say, the system should always do this no matter what. The system should never do this no matter what. We call those properties. And then you let the system work, you run some behavior against it, you run some transactions, and you observe these properties of your system and see whether they pass or fail. It kind of lets you run it like your user, runs your system like your users of your system would. Property-based testing sounds great. It comes out of academia. And so, like a lot of things in academia, it's like, sounds great, but how do we do it? And the academics just say, you just do it. It's easy. But it isn't. A lot of times, it hasn't been that easy. But if you use we think that if you use assertions, you can start introducing property-based testing into your workflow as you have it right now. Assertions let you define properties inside your code because what they let you do is they let you say, here is what should be true in this part of the code at this point in time, whatever happens. Which means that you get to state explicitly what is true about your system at all times, which is essentially you're writing a property. And you can write it all over the place. So if we think about these guarantees that we were talking about before, let's make it a little bit more practical. So this no written message is lost. Sounds great. How do we make it into an assertion? So we can try property-based testing. Well, this Kafka guarantee, no written message is lost, it has implications for both the producer side and the consumer side. On the producer side, what this really means is that messages are only written after all brokers acknowledge that they've received it. On the consumer side, what it means is all messages that were produced to the cluster can be consumed by the consumers. And so breaking these guarantees, like these high-level guarantees of our system down into actually actionable statements helps us to then take the next step to write assertions and understand how our system is running. So Connor's going to go through an example with a little bit more in detail.
Thanks, Lawrie. So we're going to look at an example of property-based testing from a real Kafka workload. I'll share some more details about where this was used. But before we go into this example, I do want to give one caveat. I'm sure we're all excited to look at code here, but we probably don't want to see dozens and dozens of lines of Rust code on the slides. So we have simplified this down into some pseudocode. But the assumptions that we're making is we're testing for some of Kafka's strongest consistency guarantees. So the assumptions here are that the number of minimum in-sync replicas, or ISRs, is equal to the number of brokers. Produced messages must be acknowledged by all brokers. There are no producer or consumer timeouts. Idempotency is enabled. And we don't see it reflected here, but we're using consumer groups in this real workload. So the nice thing about the properties that we've defined, no written messages lost, is that these are things that we can validate client side, which is a great place to start for property-based testing. So let's define a couple functions here. The first is a produce message function. And here's the skeleton of this message where we'll define our assertions, which in this case will act as test properties. The first thing that we're going to want to assert is that the producer can connect to the target cluster. And this seems simple, but it's still useful. As Lawrie said, assertions state explicitly what you believe to be true about your system at that point in time. So a failed assertion can mean either that your understanding is wrong or your code is wrong, and both are good to know. So beyond that, let's also assert that we can produce messages to this target cluster, and let's keep track of the messages that we've produced. So let's do something similar on the consumer side here. We've got a consume message function with this skeleton, and similarly, we'll want to assert that we can connect to the target cluster and that we can consume messages from the target cluster. So these assertions will act as test properties. All right, now let's bring it full circle. We have our produce message function that produces messages and keeps track of what's been produced. We have our consume message function that consumes messages from a topic and keeps track of those. And what else can we do then? We can validate that we've never lost any messages. So in this case, we can confirm that the number of produced messages is not greater than the number of consume messages, and there are no messages lost. But that's not all. We can also assert that the number of consume messages is not more than the number of produced messages, meaning there were no unknown messages, right? With this consistency model, anything that has actually been persisted to the cluster should have gotten an acknowledgement to the producer, and therefore we should have kept track of this. So here's an example of how with property-based testing, it's not easier to just add new test cases, but each test case can actually build on top of itself. So this was an introduction into using property-based testing, which allows us to assert what's true in any condition, regardless of what has happened previously or what else is currently happening. But how do we create these good conditions? How do we ensure that our properties actually matter? Well, this is where autonomous testing comes into play. Autonomous testing is using a computer to generate test cases and explore a software system. So what exactly does this mean? Well, let's go back to our friend Mario for a concrete example. So in the original Mario game that Lawrie previewed earlier, Mario has a couple of moves. He can advance right at some velocity, he can jump up at some rate, and he can hit blocks that are above him. He can do these moves in sequence or in parallel. So one path that he might take through this particular level looks like this, which he happens to beat. But using the principles of autonomous testing and doing these moves, again, in sequence or in parallel, Mario can explore a bunch of different paths through this particular level. So here we can see what these paths through that level might look like. Let's look at the next level, same deal here. This is one path that Mario can take, a happy path, if you will, as he's beating this particular level. But using the concepts and principles of autonomous testing, we can explore a bunch of different paths with Mario and get to different points on the level. So this is all well and good, but we want to give you some best practices for using autonomous testing when testing your own software. So we've got 3 recommendations. The first is to try everything sometimes. So when testing a system like Kafka, this means try all the ways in which users can interact with your system, like all the various API calls. Secondly, use randomness. Users can interact with your system in unforeseeable ways, so account for that when designing your test cases. And third, notice misbehavior when it happens. We want to continuously validate so that we can identify property failures as soon as possible. All right, so let's build on the Kafka examples I shared earlier. As a reminder, we developed 3 functions: produce message, consume message, and validate. So let's see how autonomous testing can use these functions to generate test cases or test paths. One possible test path, of course, is similar to the example-based example that we saw earlier. We produce a known message to a known topic, we consume messages from a known topic, and then we validate. And this is a good start. We can expand on this by producing known messages to a known topic in serial, and then consuming those messages and validating, which is still good. But let's add some of these actions in parallel. So we can produce messages at the same time to the same topic, and then consume messages from that topic. But we shared with you some best practices for using autonomous testing, so let's take a look at those in action. So here's another test path, and walking through some of how our best practices are reflected here. We said we want to try everything sometimes, right? So as opposed to just using produce and consume functions, let's also use some of the other API calls in Kafka, like rebalancing consumer groups, deleting topics, altering partitions on a topic. Let's add randomness. Let's produce random messages to a random topic and randomly consume messages from known topics. And when we're using randomness, it's not just for the shapes and targets of data, but we should also use randomness for the number of parallel processes, the number of parallel threads, the order and sequence of these tasks. And lastly, we want to continuously validate. So as opposed to validating at the end whether everything is correct, we want to be regularly validating so that we can pinpoint and narrow down where issues were introduced. So let's take another look at how we're testing this Kafka cluster here. We've got our producer and consumer interacting with the cluster. Another important layer here is the environmental factors. So let's add some environmental factors or faults in as well while we're testing. So some of the things that we'll need to account for when we're running a Kafka cluster in production is that we'll need to handle network latency, network partitions, node and process crashes or hangs, resource constraints, and all of these are important to add into your autonomous testing scenarios, especially against distributed systems like Kafka. So these are important for 2 reasons, right? First off, during autonomous testing, we want to try everything sometimes, and this way we ensure that we're testing our failure cases. And secondly, we know that with distributed systems, the most critical issues happen due to mishandling of failure cases. So we'll want to ensure that those are well tested. So after walking through these examples, we can see how property-based testing unlocks autonomous testing. We can assert even simple properties, such as the ability to connect to a cluster or produce messages regardless of what's happened previously or what else has currently happened. And these properties can continue to build on one another with confidence that each one's being thoroughly tested. All right, so this is all great, but how can we explore these test paths? Well, this is where Antithesis comes into play. Antithesis is an autonomous testing platform that tests for properties of entire systems. And let's see what it looks like in action, first again with Mario. So let's see if this plays. Yes. On Antithesis, we can explore dozens of scenarios in parallel. In this case, we see Mario is playing 16 different levels at once. On the Antithesis platform, we can actually explore many more than this in parallel. And while exploring all these scenarios, we also have a feedback mechanism that allows us to continue to seek out interesting scenarios. So we saw initially Mario was on level 1, just falling into one of the first bunkers there. But as time advances, he's advancing to newer levels, and we're seeing different parts of the game. So this is what we really want to be able to do, is explore some of those more interesting states of the game and the systems that we're testing. because we know that in those interesting, novel scenarios, those edge cases, that's where issues and bugs are most likely to lie. So we're going to take a look at World 8, Level 4 of Mario, one of the underwater levels. And if we recall back to what Lawrie had told us about some of the guarantees of Mario, we know that one of the guarantees is that he should not be able to move through obstacles. So let's take a look at what happens here. Mario is moving along. Oh, he is going through the wall, which is not supposed to happen. So it looks like here we have found a bug in Mario. So that's pretty exciting and shows the power of the Antithesis platform, how we're able to explore and seek out these interesting scenarios to find these issues before users do. But, you know, a bug in Mario is not too consequential, right? And I think if we were playing Mario, it would be actually kind of fun to know where we could shortcut through some of the obstacles. But finding bugs is not always fun for a lot of our users and customers that test on Antithesis regularly, such as the streaming and infrastructure products that we've heard about today at the Data Streaming Summit. So here's an example of some of the customers that work with Antithesis to use our platform to find some of their thorniest issues before their users do in production. And beyond these customers, there's one company in particular that we want to highlight, and that's Stream Native. So we've worked with the Stream Native team to test Ursa, which, as we know, is their Kafka-compatible offering. We tested a 3-node Ursa cluster with an Oxia metadata store and an object storage node. So we used the same 3 test cases that we walked through earlier, producing, consuming, and validating, with a lot of the caveats that I had mentioned earlier, and this workload is available on our public GitHub. Over the course of a couple weeks testing Ursa, we explored over 100,000 unique scenarios across several different Ursa versions, and we helped the Stream Native team find and fix novel issues surrounding some of Kafka's common safety properties that we talked about today, specifically no lost messages, no unknown messages, offsets always increasing, and consistent data being read at the same topic partition and offset. So this has given the Stream Native team more confidence in their Ursa offering and has allowed them to ship high-quality code to their customers faster, and we look forward to continue working with the Stream Native team to empower their ambitious products and features. We heard earlier today from Pengwei Li, who's the Director of Platform Engineering at Stream Native. We worked closely with Pengwei during this engagement, and I'm sure Pengwei would have a lot more to share about how this testing went on the Antithesis platform. So to wrap things up today, we covered property-based testing and how we can write assertions to service test properties. We covered autonomous testing and how we can autonomously construct and explore test paths. And between these 2 concepts and the success story of Stream Native testing Ursa on Antithesis and what we saw with Mario on Antithesis, we hope that we've inspired you to rethink how you do your testing so that you can be more confident in your software guarantees. Thanks, everyone, for your time. If you're interested in learning more about Antithesis, please scan this QR code. Come find us after our talk or find us tonight at the happy hour. In the meantime, does anyone have any questions?
So what are some things you found interesting for testing beyond code? It's very hard to test things that are completely non-deterministic, like AI agents and LLMs and that ilk of things. But maybe there's a way to apply it there. The other one is applying it to maybe closer to home for folks here, integrity of data structures and the data in the warehouse, you know, the unreasonability of saying no negative quantities or that sort of thing. And last might be the thing I'm closest to, which is security configurations, right? That things are indeed being broadcast and updated correctly and the messages are getting there, but the actual result is that nobody has access to this thing right now. It's an emergency, right? That you're looking for contradictions of that nature. So I just didn't know whether Antithesis property-based testing had been applied to other areas as well than just testing kind of essentially system software services for either data integrity or for logical properties about security or for LLMs and AI systems in the loop.
Yeah, so good question, thank you. Most of our customers are testing distributed systems and have properties around safety and liveness. But we've got assertions available in a number of different languages, and any condition that you can express as an assertion, you can use that as a test property. So we've seen customers also have test properties for security around some of the conditions that you talked about, right? Role-based access and whatnot, confirming that users can only see data that they're intended to see. And then to address your question on LLMs and agents, this is something that we've tested a lot of AI infrastructure. So some of the underlying components of the models that are running, but we have not done as much testing with the actual LLM models themselves. Does that answer your question?
We have done some testing with like financial services for ledgers and business logic kind of things, and I think some of those learnings would apply, but we haven't done the LLM testing yet. I'm sure it's coming.